Hi, welcome at DevSecCon. It's a pleasure to be here. I'm Philippe Ryck from Belgium. I'm actually presenting from Belgium this time, which is kind of weird, but we've gotten used to it over the past year and a half, I would say. Nonetheless, I'm still looking forward to real events, real conferences where we can actually see people following talks and stuff, seeing computers and walls and stuff like that. But hey, that's what this is all about, and let's do what we have to do in the circumstances that we have here. So let's talk about token security in single page applications. That's basically going to be the setup for the next 30 minutes. And I'm going to walk you through a couple of scenarios to discuss some kind of a nuanced problem where there's no real one size fits all answer. So if you were hoping to find final answers in this session, I'm going to have to be disappointing because it's not going to be like that, but I'm going to give you some options and help you think about this challenge in modern single page applications. Let's start at the beginning. Let's start talking about local storage, because if you're going to look at token storage solutions, you'll find people saying like, yeah, local storage is awesome. And you'll find other people saying like, oh my God, never put stuff in local storage. And the truth is somewhere in the middle. So local storage is this browser-based storage area. It's basically a fairly simple mechanism. It has key value storage. So you basically set an item and you get an item with a key and a value. That's as simple as things get. Storage-wise, this is really easy to use. It's not the browser developer's favorite API because of some performance issues, but nonetheless, it actually works really well for storing something simple like a token. And you may have found some advice that says like, yeah, this is cool. And you'll find people saying like, yeah, not really, this is dangerous and you should never do that. And that's what I want to talk about in a couple of minutes. Before we get to that, a small word about myself. I'm Philippe Ryck. I used to travel the world to help companies with complex security problems. So I do developer training where I help people understand vulnerabilities and defenses, but I also do specialized consulting on topics like exactly this one, or OAuth and OpenID Connect and all of these fairly advanced and complicated technologies. So if you want to know more about that or about me, there's a website, Pragmatic Web Security. That's my company. You can find all information there. And of course, you'll find me online as well. But enough about me. We only have 30 minutes. So let's talk about token security. Let's talk about the dangers of local storage. So the thing is, and people are kind of right about that, storing data on local storage is making it easy for the attacker to grab that data if something goes wrong. So let's assume that the attacker can exploit a vulnerability in your application, allowing the attacker to, for example, execute code through a cross-site scripting vulnerability, or to compromise a advertisement that you load and all of a sudden code executes in your application. That's the red block on this slide. That code can read local storage. And if you put sensitive tokens in that local storage area, an attacker able to inject some code in your application will be able to read that code, ship it off somewhere else, and off you go. And that attack is really, really easy. As in, the code to do that is exactly these two lines of code. And I'm sure you can write that as a single line of code as well, just a little bit less readable, but you get the idea. So this is not a new attack vector. This is not something that should be shocking to you. This is something that's very well known, like, yeah, we can do that. And that's why you'll find advice that says like, yeah, you should never put stuff in local storage because an attacker can steal it from there. And since this problem is well known, you'll find defenses built into technologies like OAuth, which try to counter these attack scenarios. For example, in OAuth world, your single page application would use tokens, an access token to access the API, and a refresh token for long-term access. As in, your access token is valid for 10 minutes, so you use it for 10 minutes, and then afterwards you use a refresh token to get a new access token, and you do that again and then again and again. And that access token is very sensitive. It gives access to the API, but the refresh token is even more sensitive because a refresh token gives the attacker the ability to get new access tokens over and over again until it expires. The thing is, in an OAuth scenario with a backend web application involved, this refresh token is kind of secured quite well because it's stored on a server and it can only be used by the application which authenticates. But that doesn't happen when you use refresh tokens in the browser. And that's kind of a new development, development in the last 2 years, basically. And such a refresh token in the browser is a bearer token, which means that anyone who gets hold of it, an attacker stealing it from local storage, will be able to use it, which will give the attacker eventually access to an API on behalf of the user. And that's something that we might want to avoid. So in the OAuth world, The specifications state that refresh tokens that are used in front-end applications like a web app, they should require additional protection. And concretely, in a browser-based environment, that protection is something called refresh token rotation. And refresh token rotation works as follows. I'm going to explain that with a timeline because that's the easiest way to visualize this process. So the application, the front-end app, uses a legitimate OAuth flow to obtain tokens, AT1, access token 1, and RT1, which is refresh token 1. And access token 1 expires after X amount of time, let's say 10 minutes. So what the application is typically going to do, it knows this. It says like, yeah, in 9 minutes, in 9 minutes, it says like, yeah, my token is about to expire. You know what? I'm going to get a new one. And because of refresh token rotation, the app uses a refresh token, RT1, and receives a new set of tokens, both access token and refresh token, AT2 and RT2. And again, AT2 expires in 10 minutes. So in 9 minutes, the app does the same thing with refresh token 2 to get token set 3, and the same 9 minutes later with token set 3 to get token set 4, and so on and so on. This concept of refresh token rotation ensures that a refresh token, RT1, RT2, RT3, and RT4, can only be used once. That's the whole point here. So the idea is that if somebody steals it and it would be used twice, then we know that something is wrong and we can actually take some defensive action to ensure that we can limit abuse. And that scenario would look like this. So the application is just doing what it does using refresh tokens. And at some point in time, the attacker injects or succeeds in executing a piece of malicious JavaScript code in the application. And the attacker is going to steal stuff from local storage, and there's a refresh token in there, and the attacker is like, ooh, interesting. I have now a refresh token, which is linked to this application and this user. So what if I just use RT2 so I can get AT3 and RT3? And that's going to work because that's how bearer refresh tokens work. So the attacker at that point has a token, AT3, allowing it to access an API on behalf of the victim, which is a big problem. But, and this is the kicker of refresh token rotation, the application doesn't know that this has happened. Otherwise, they would have prevented the code from executing in the first place. So the application is kind of oblivious here. And at some point in time, it's going to go to the authorization server in this case with refresh token 2 and be like, hey, can I get new tokens, please? And at that point, the authorization server sees RT2 being used again, the second time. And it says like, oh, no, this is not good. That's the whole point here. Refresh tokens are only supposed to be used once, so we can detect theft of a token and we can take corrective action. In this case, that means we revoke all the tokens associated to RT2, which prevents the attacker from using RT3 or 4 or 5 or whatever token that the attacker has. And that's the concept of refresh token rotation. Now, there's a very big problem with this approach. From a high-level perspective, this seems to work quite well. But what this approach fails to understand is that the attacker can do a hell of a lot more than simply steal data from local storage. And that's why you find a lot of people focusing on this local storage like, oh my God, they can steal data. And they completely forget that the attacker can do all kinds of other dangerous things. It's not a single event. It's not steal data and abuse that data afterwards. The attacker can manipulate the application any way they want. I will come back to that in a second or in a couple of minutes as well. So this first takeaway is really important. It's a very common misconception that cross-site scripting or malicious JavaScript code is a single event, one point in time, while it can be a continuous, ongoing attack. That's essentially takeaway number 1. So if we have this problem with local storage, let's look at an alternative. Why not look at something else instead? And let's look at cookies here. Cookies are very old. Lots of people don't like, well, people like Christmas cookies here, but lots of people don't like cookies in the browser. And for some good reasons, but also, well, they are what they are, and we have to deal with them anyway. So what's the deal with cookies here? Well, cookies are kept in a cookie jar. So conceptually, this looks very similar because it's a storage area in the browser. The difference is it's not code, or your application code doesn't have to put cookies in the cookie jar. The browser does that by itself. But cookies can be accessed from JavaScript. So your code on the left, the blue code, can read a cookie from the jar, But if something goes wrong, the attacker can use a malicious payload, which is almost exactly like the one we covered before, to read that cookie jar as well. And again, that's a well-known problem. That's something we've known about for 20 years or something. It's like, oh yeah, that's a problem. And the fix for that in the cookie world is a flag called HTTP only. And that HTTP only flag basically tells the browser, this cookie is for HTTP traffic. It should not be accessed from JavaScript. And adding that simple keyword to your cookie configuration when you set a cookie will ensure that malicious code can no longer access that cookie. Awesome, right? I mean, this is a cookie that can never be stolen through malicious JavaScript. Wonderful. And again, from a high-level perspective, you might think like, oh yeah, that's a good solution, which you'll often read about as well. Like, yeah, just use this because it's better. But if you investigate the security properties of what's really going on, the security is kind of crap. I mean, from the outside, the door probably looks closed until there's a bit of wind, and then your cheetah will crack and your door will be blown wide open. And it's the same story with cookies in the browser. Because the attack vector is not a single instance or a single occurrence of a bad thing. It's the fact that the attacker code is executing in the application. And the attacker can do whatever the hell they want. So they can't steal cookies. Good. What else can they do? They can steal data from the page. If it's a payroll application and the attacker can execute code, they can just scrape all the data and send it off to someone else or to a server controlled by the attacker. They can steal data from the application. They can modify the UI. Banking Trojans love to do this. They add a transaction in an online banking app and they hide it from the user. They just modify the UI as if the transaction was never there until you sign your transactions and boom, off goes your money. Kind of dangerous. And the attacker code can start sending requests to a backend, and the browser will attach cookies on those requests. And the backend server will have no way to distinguish between a request coming from the red code, the malicious code, or the blue code, the non-malicious code, because it all runs in the same environment. And that's the real threat of cross-site scripting, of malicious JavaScript code. The attacker can do whatever they want once the code runs in the application. So with unstealable cookies, I know unstealable is not a word, but it kind of expresses what I want to say here. So if unstealable cookies are not secure, because we have things like session writing where the attacker can send requests with cookies anyway, what does that mean for tokens that are not kept out of reach for the attacker? Well, the story isn't very good, actually. Here's one attack scenario that circumvents refresh token rotation altogether. So the app does what it did before, handles tokens. And the malicious code is injected at some point in time and steals the latest refresh token. But it doesn't use it. It just steals it and it sits on it. And the app notices that the token is about to expire, so it requests a new token. Use RT1 to get AT2 and RT2. And the malicious code sees like, ooh, you got a new refresh token. That's good. Let me steal that one as well. I'm going to steal it, but I'm not going to use it. Just going to send it off somewhere else in case we want to use it later. And then the attacker code detects that the user has closed the application. You can listen to close events, or you can have a heartbeat mechanism that sends a request every 10 seconds. And if that stops, then it's fair to assume that the application of the user has gone offline, that it has been closed. And at that point, the application is no longer running in the browser of the user. So the application is not going to use the latest refresh token, RT2. So the attacker can now be like, ooh, I'm going to use RT2. And I'm going to request token set 3, AT3, and RT3, and I'm going to get that. And there's nothing to detect here because the application has been closed and the application will never reuse RT2. So in this setup, refresh token rotation is a useless defense, just because we made the attacker a little bit smarter and made the attack a little bit more sophisticated. That brings us to takeaway number 2. Takeaway number 2 says that the attacker can do anything that you can do as a developer. So if you can think of something as a developer, the attacker can do exactly the same thing in the malicious code because the attacker has the full privileges that you have as a developer once that code executes. And that's a very, very important thing to realize. So what can you do then? Well, not much, actually. Sorry about that. Well, we'll get to a couple of solutions in the second part of the presentation here. One of the things you can do is you can make it a lot more difficult, or you can reduce the number of things that can go wrong. And one way to do that is the use of a web worker. And that's actually what some of the advanced OAuth SDKs are doing. This example is based on the Auth0 SDK, which is how you would implement OAuth flows for Auth0 in your front-end web app like Angular or React or whatever. And that SDK, once you load it, it's a piece of JavaScript. That SDK will launch a web worker. And a web worker is a fully isolated environment in the browser that can run in parallel with the main application. So it can do some calculations, it can send requests. And in this case, it's going to keep that refresh token in a secure, isolated environment. So the steps here would be the SDK is bootstrapped and it starts an OAuth flow. Don't worry about those details. And it's going to ask the worker to handle the final step of that flow, which will result in tokens. So the tokens are, the worker handles that. The tokens are returned in step 4 and are now available within that web worker, nowhere else. In that web worker, the refresh token is kept securely, and the access token, the one that is used by the application to contact APIs, that one is shared back with the main application. So the application only has an access token, no refresh token. What if we need to use a refresh token? Well, the application will ask the web worker to use its refresh token. The web worker will run a refresh token flow with the authorization server, get new tokens in step 8, keep the refresh token, and return the access token to the main application. And that's essentially how you would use a web worker in practice. A very solid isolation mechanism, fully handled within the browser. So it doesn't require too much code to use or benefit from this isolation. That's actually pretty awesome. This is a really good pattern, by the way. This is a job well done by the library developers. This is absolutely great. So sensitive tokens are only available in the worker. There's no advertisements, no third-party code, no nothing in that worker. So this is actually a pretty secure environment. And we use the web messaging API to enable interaction. So this is takeaway number 3. This is actually a really good pattern to isolate sensitive functionality from the main application context. It doesn't really solve the full problem, but it makes it a lot more difficult or even virtually impossible for the attacker to steal that refresh token from that worker environment. That's a good approach. That's a good solution. However, like I said, not an easy topic. We still expose the access token in step 5 and 9. So if malicious code runs in the application's context, it can still intercept and steal those access tokens, even if you try really hard to not expose them. I actually wrote an article about that on my website, so you can look this up and find that. Even if you try to hide it, there will be a way for the attacker to override JavaScript functions through prototype pollution and steal that information one way or the other. So brings us back, we're going to go backwards one step to takeaway number 2. If you can think of something, the attacker can likely do the same thing in their code as well. It's really, really, really hard to isolate tokens within a JavaScript environment if you don't have browser-enforced boundaries like the web workers boundary in our example from before. It actually gets a little bit worse, because if the attacker can do all of that stuff, what else can they do? And there's a scenario that quite frankly scares the crap out of me, where the attacker doesn't even touch the legitimate application's tokens. So your legitimate application, your front end, handles running of an OAuth flow with the authorization server. That's step 1. Well, in reality, step 1 is actually like 15 steps or something, but don't worry about those in practice. But in the end, the application is going to get tokens, maybe with the SDK and the web worker and fully isolated and so on and so on. However, during that process, during that flow, somewhere the authorization server has stored a cookie in the browser to enable things like single sign-on and remembering a session and so on and so on. So that's the authorization server where the user would have authenticated. That one still relies on cookies under the hood to keep track of a session one way or another. That's the legitimate setup. That's how all of these OAuth and OIDC implementations work in practice. Now, our attacker. The attacker injects a piece of malicious JavaScript code. Remember, the application is doing its thing. It has an access token and a refresh token, but the attacker is like, yeah, I don't care. You do you, I'll do my thing. And the attacker in this case will set up a listener to receive messages from a frame. That's a technical detail. And it will run a new flow in a frame. The frame is the box here. That frame is hidden. It's called a silent authentication flow because it's a background frame that's invisible to the user. And in that frame, the attacker will run a flow with the authorization server. And in step 4, there's something very crucial happening. Because of how this protocol works with the cookie kept by the browser will include that cookie in step 4. That's how the authorization server knows who the user is. When I'm running this in my browser, I'm going to authenticate as Philippe in step 1. And in step 4, the authorization server like, I know who you are. You were Philippe 10 minutes ago. So welcome back. And it's not going to ask me again. It's just going to return tokens, well, a code, which are tokens, and so on and so on, giving the attacker a new set of tokens in step 6. That's basically what happens here. Because if you can do it, the attacker can do it. That's a key takeaway here. If you can do something, like running a flow in an iframe to get tokens, which is supported by OAuth, the attacker can do the same thing, and there's nothing you can do to stop that. Key takeaways, 3 very important things. Malicious code can do a lot more than a single action. That's a very, very common misconception, even in a world of OAuth where a lot of smart people are building specs. Even there, defenses often focus on this one problem instead of looking at the bigger picture of what malicious code can do. Malicious code can do anything a legitimate frontend can do. Anything you can think of is possible. The best piece of advice I have here is focus on cross-site scripting mitigations, prevent the execution of the malicious code in the first place by following secure coding guidelines and applying defense in-depth mechanisms like trusted types and content security policy, and so on and so on. All right. Well, I'm not done yet. This would be a very depressing end. So these were the key takeaways so far. I have one more topic I want to discuss, which gives us a bit more hope towards the future. So how can you handle tokens securely in a front-end application? Well, honestly, you can't. That's the conclusion here. You cannot do this because if your application runs JavaScript code and the attacker runs JavaScript code in the same environment, there's no way to isolate these from each other in a practical way. So the solution that we often use in practice for sensitive single-page applications is to not handle tokens in the browser. We keep them on a server component, which we call a backend for frontend, or a BFF in short. And a BFF is a, I want to say dumb, but that's not the right word, a very, very non-complicated component that doesn't do anything business logic related. The only thing it does, it's kind of a reverse proxy between the frontend and the API. So our BFF becomes the client application in an OAuth flow. So it basically, that's the part that will request tokens from that authorization server and keeps those tokens in a secure location. Tokens are handled in the backend, much better security properties in the browser. You don't have to drop them in local storage or whatever. And what's even better is the refresh token used in this scenario can only be used by that backend application. Even if somebody steals it without the credentials of that backend application, that BFF, an attacker will not be able to abuse those tokens. Good. How do the frontend and the BFF communicate? Well, you typically run these in the same domain. Restograde.com/BFF would be an endpoint for the BFF. So if it runs in the same domain, you can easily use cookies to track state. And cookies doesn't necessarily mean it has to be a stateful backend application. You can also use encrypted cookies that store data on the browser. What's important is that this BFF is the only one able to extract the data from that cookie, validate it, and use it in practice. How would you send a request to an API? Well, the frontend sends it to the BFF in a request carrying a cookie, and the BFF will unpack that cookie, find the tokens, use or make sure the tokens are valid, and then send a request to the API. That's essentially how this would work in practice. And the response from the API, of course, would be propagated back to that front-end application, making it possible to do whatever it wants to do. And in a nutshell, this setup, this scenario, doesn't really change much on the front-end side. Actually, your front-end gets easier. You can take out the OAuth stuff, throw it away, and change the endpoint for your API calls, and that's it. That's the only thing you have to change. Everything else remains the same. And on the API side of things don't change either. The API all the way on the right just handles a request with an access token, just like it did before. And the authorization server doesn't really change. It's a different type of client, but that's just a matter of configuration. So all we need is a simple BFF component, well, simple, this BFF component that is able to translate a cookie value into an access token, essentially. Brings us to takeaway number 4. BFFs keep tokens out of the browser, which significantly increases security. That's the reality. Yes, it's less fun. Let's use the nice word here. Less fun to build a BFF and deploy that because it's an additional component, but it's also not a very complicated or large component. And it's a component that can be easily reused across different front-end applications because it always does the same thing, basically. There's one attack vector that doesn't go away, and that's a session writing problem. That's if somebody injects malicious code into the front end, they can still send requests to the BFF pretending to be the legitimate application. That's the same challenge we had with cookies before, and that's a challenge we can't solve in any way. However, with that said, what happens in this setup is that all requests have to go through the BFF. So you have an additional point of control that can observe all requests. So it could see weird things. If the application sends requests like once every 10 seconds, and all of a sudden you get a burst of requests for 10,000 requests in 5 seconds, the BFF can assume that something is wrong, that maybe somebody is trying to extract data from the API or something like that. And that would be a way to detect that and maybe prevent that from happening. So the BFF reduces the attack surface, but it never takes the session writing problem away altogether, which means you still have to focus on secure coding guidelines and defense in-depth mechanisms. And that brings me to the real takeaways here. If you're building a non-sensitive single-page application, I would say you can handle tokens in the browser. The approach with refresh token rotation, it's not bad. It's just not as secure as we would like it to be. So if you're building something non-sensitive that doesn't handle personal data, financial data, whatever, then sure, just use the best practices for OAuth and you're good to go. If you're building something sensitive, healthcare apps, business apps, something like that, strongly consider to keep tokens out of the browser with the BFF. It's the only real way of ensuring that malicious code cannot simply request new tokens and ship them off somewhere else. And thirdly, you can, if you use a BFF, you can detect and block illegitimate traffic patterns. You can reduce the number of API endpoints that can be accessed, and so on and so on. So it gives you more control if you want to get that done in practice. All right. A couple of references to wrap up. The article I mentioned, the link is right here on the slides. There's also a link to a BFF middleware for .NET by Duende. It's a really good approach, a good library. So if you want to see a concrete implementation of middleware for building BFFs, definitely check it out. And if you want to learn more about the intricate details of OAuth, and trust me, there are a lot, I also have an online course that you can join to learn all about the current best practices for OAuth and OIDC in single-page applications and in API world. And with that, I want to thank you for watching. I want to invite you to connect with me on Twitter and LinkedIn. And if you have any questions, you can always ask them in the conference environment after this session. All right.